In this chapter, we will go over solutions, their concentrations, and their colligative properties. So to start, solutions are homogeneous mixtures, and they are made up of two or more substances. The components of these substances can be present as atoms, as molecules, or as ions. So when you look at a solution and you see that the solution is transparent, what does that mean? It means that the particles in the solution are too small to reflect light. And this is why the solution appears to have no color. And remember that particles, they do exist in solution. And particles, they are in constant motion. So they are moving constantly. However, they are so small that they do not precipitate. So you don't see any precipitation in there. This is why you see like a homogeneous solution in there that is transparent. So a solution is made up of two components. It's made up of a solvent. So the solvent is what dissolves the solute. Like for example, if we have salt in water. So let's put an example in there. So example, if we have salt and we dissolve it in water, you know that salt is sodium chloride. So you do have Na plus and Cl minus in there. So the salt is going to be your solute. So the salt is going to be the solute, and the water is going to be your solvent. So by definition, solutes, they are less quantity than the solvent. So a solute of a solution is any substance that is present in an amount that is less than that of the solvent. The solute and the solvent will make up a solution. So I would say that the salt and the water, both of these, they are going to make up a solution. Okay? Now, solutes can be either solid, they can be liquids, they can be gases as well. So let's take, for example, if you have sugar, it doesn't matter how much sugar in there. Sugar is solid, right? So if you take sugar, a teaspoon of sugar, and you dissolve it in water. So the sugar is going to be completely dissolved in water. There's no precipitate in there. So I would say that this is a homogeneous solution. The sugar is going to be the solute. The water is going to be the solvent. See, the solvent is in more quantities or more amount than that of the solute. So the water is going to be my solvent. And I would say that the water and the sugar, which is the solvent and the solute, they're going to make our solution, which is homogeneous. On the other hand, if you mix oil and water, we all know that oil and water, they do not mix. Why? Because oil is organic, water is aqueous. So they're going to make two separate phases in there. The oil is going to float on the top of the water surface because the oil has less density than water. Water is denser, so water is heavier. So this is why water sinks and oil floats on top. We would say that oil is going to be our solute because it occurs in less quantities than that of the water. Water is going to be my solvent, and the oil and the water, they're both going to make our solution, but our solution here is not mixed. So I would say that those two are going to make a non-homogeneous solution. Another example, if you dissolve alcohol in water, alcohol dissolves in water, and they will make a homogeneous solution. Alcohol is my solute, and water is going to be my solvent. So the physical state of the solution, whether it is a liquid, a solid, or a gas, always follows that of the solvent. So this is why you look at the solvent and you see what physical state is the solvent is, then your solution is going to have the same physical state. So if your solvent is a solid, then in this case, the solution is going to be a solid. And if your solvent is a liquid, then your solution is going to be a liquid. And if your solvent is a gas, then your solution is going to be a gas. Let's have an example. Like if you have a copper solid, so if you take copper solid and you dissolve it in gold solid, so you look, you see that your solvent is gold and your solvent is solid, then the solution is going to be solid. On the other hand, if you take hydrogen gas, which is a solute, and you dissolve it in palladium, which is a solid, then your solution is going to follow the physical state of that solvent, which is a solid. Air is gaseous. Air has a gaseous state. Why? Because the solvent in air is nitrogen. So air, we know that it's made up of oxygen, carbon dioxide, hydrogen, but it's made up more of nitrogen. So nitrogen is the solvent in air, and nitrogen is gas. So this is why air is a gaseous solution. Solutes are represented by their solubility constant. So the term solubility is given to represent the maximum amount in grams of a solute that can be dissolved in a specific amount of solvent at a specific temperature and a specific pressure. This is a plot of the solubility of three solutes. Glycerin, which is a liquid, sodium chloride, lithium sulfate, these two are solids. The plot of the solubility, you can see that it's a plot of the temperature versus the solubility. So we expect that the solubility to change as the temperature increases or decreases. Okay, so the temperature has a big effect on the solubility and the pressure as well. Here I'm reporting the temperature. So let's say, for example, if we are looking at room temperature, like 25 degrees. So you want to check the solubility of lithium sulfate at 25, the solubility of sodium chloride at 25, and the solubility of the glycerin at 25. So all what you need to do is just extrapolate in there. So this is a glycerin. At 25, it's around 28 grams of glycerin in 100 mils of water. This is its solubility. So if you add more, at room temperature, it's not going to dissolve. So let's say if you add 30 grams of glycerin in 100 mils of water, those additional 2 grams, they will not dissolve. They will precipitate. Unless you increase the temperature of the water, then the additional 2 grams will dissolve. So this is what solubility means. It's the cutoff or the maximum amount of mass of the solute that you can add, and still the solute is dissolved in the solution. But again, you would need to record the temperature that you are working with. So for, let's say, for example, for the lithium sulfate. So for the lithium sulfate, we are looking at around, let's say, around the 25 grams in there. So for the lithium sulfate, it's around the 25 grams at room temperature. And as you can see, the solubility decreases as the temperature increases. So here the solubility decreases as the temperature increases for the lithium sulfate. So it's not always necessary that as the temperature increases, the solubility decreases. No, the solubility increase, I mean. No, here we do have it opposite there. For the sodium chloride, we can see that the solubility, let's extrapolate over here. So that is around maybe 37 grams, okay, per 100 grams of water. So I would say, okay, if I want the sodium chloride to dissolve in water at room temperature, I have to add a maximum amount of 37 grams. If I add more, the additional grams, they will not dissolve unless I increase the temperature of the solution. So I can see over here that the solubility is increasing slightly as the temperature increases. So we would say that solubility increases slightly as the temperature increases. For glycerin, at 25 degrees, if we extrapolate for glycerin, you can see over here that the maximum that I can add is 28 grams and 100 grams of water. This is at 25 degrees. So this means that if I added more, I would need to increase the temperature to allow this additional amount to dissolve. Glycerin solubility increases strongly or significantly when the temperature is increasing compared to sodium chloride. So the solubility of the glycerin increases strongly when the temperature increases. So let's define the terms soluble, insoluble, and miscible. Soluble and insoluble are used to define the solubility of solid solutes. If you have a liquid solute, then you're going to use the term miscible. So the term soluble is given whenever a solute is completely dissolved in a solvent. So let's take sugar, for example. Now, if you look up sugar, in 100 mils of water, so in 100 mils of water, water can accept only 200 grams of sugar. I cannot accept more. So if you add more than 200 grams of sugar in that much of water, whatever you add extra will precipitate. Okay? So let's say if I add 1 gram of sugar, this is less than 200 grams in 100 mils of water, the sugar will dissolve in water and the solution will be homogeneous. So the term homogeneous, I give it whenever the solute is completely dissolved in the solvent in there. And I would say that the solute and the solvent, they are soluble in each other and they make a homogeneous solution. On the other hand, if I add 300 grams of sugar in 100 mils of water, so I know that the maximum capacity of the 100 mils is just 200 grams. So there's an extra 100 in there that will precipitate. So this makes the solution a non-homogeneous solution, and it makes the 300 grams of sugar not soluble in water, okay, or insoluble in water. So the term insoluble, we use it whenever the solute does not dissolve in the solvent completely, okay? Now the term miscible, we use it for liquid solutes. For example, oil. Here I'm giving two examples, oil and alcohol. We know that oil is different than water. So when you add oil to water, oil and water, they don't mix because these are two different phases. One is organic, the other is aqueous. So oil is going to float on top of the water. Why? Because of its density. We said that oil is lighter than water. So water is denser. So water is going to sink, oil is going to float. They're going to make two separate phases in there. An organic phase, which is on the top, and an aqueous phase, which is on the bottom. So these two phases in there are going to make a non-homogeneous solution. A homogeneous solution is one phase, like water. So when you have two phases, this is a non-homogeneous solution. On the other hand, if you take an alcohol in there, 10 drops or many drops, you add them to the water, the alcohol is going to dissolve in water. So you're not going to have any separation of phases. So you'll see that you're going to have a homogeneous solution. We would say that the alcohol is miscible in water. Oil, no matter how much you add, 10 drops or many drops, oil is not miscible. It forms two phases, and it forms a non-homogeneous solution. There are 3 degrees of solution saturation. Unsaturated, saturated, and supersaturated. So an unsaturated solution, this is a solution where the solute dissolved is less than the maximum amount of the solvent can hold under specific temperature and pressure. We gave an example earlier of 1 gram of sugar dissolved in 100 mils of water. Well, the 100 mils of water can accept up to 200 grams of sugar, but here you are using less amount of solute. This is called an unsaturated solution. Now, for the saturated solution, a saturated solution is whenever you put 200 grams in 100 mils of water. That will be a saturated solution. So a saturated solution, this is the solution that contains the maximum amount of possible dissolved solute in a specific condition of temperature and the pressure. And then a supersaturated solution, if you go ahead and you put 300 grams of sugar in water. I know that in 100 mils of water, I can accept only 200 grams of sugar. So that 100 grams of sugar remaining, this will precipitate. So that will make this a supersaturated solution. Now, can you dissolve this solid that is extra in the 100 mils of water? Yes, you can, by increasing the temperature of the solution. So if you increase the temperature of the water, then the extra solid will dissolve. But pay attention when when the temperature of the water cools back to room temperature, that same amount will precipitate again. So by definition, a supersaturated solution, this one is unstable. That's why we said unstable, because whatever you force to dissolve is going to precipitate again. So it's an unstable solution that contains an amount of solute greater than the solute solubility under specific temperature and the pressure. This picture over here represents the three degrees of unsaturation states: unsaturated, saturated versus supersaturated. So unsaturated solution, you can add your solute in there, the minimum amount of solute, and it will dissolve. Saturated solution, you're going to add the maximum amount of the solute and it will dissolve, beyond which you cannot add more. Okay, if you added more, then whatever you add is going to go ahead and precipitate. You can force it to dissolve by increasing the temperature of your solution, of your solvent. But whenever your solvent goes back to room temperature, then whatever is in excess is going to go ahead and precipitate. So how does the solvent dissolve the solute? Guys, this is called a solution process, and it goes by like dissolves like. So you need a polar solvent to dissolve a polar solute. Okay, so like dissolves like. A polar solvent dissolves a polar solute. A nonpolar solvent dissolves a nonpolar solute. So let's say, for example, you have a solution of salt and water. Okay, we know that salt is NaCl. So we're going to start with the first one. This is salt, Na. Na is positive and the Cl is negative, right? So NaCl, these two are what? These two are called ions in there. These two are called ions. If I take a solution of salt and water, so you have here salt, which is Na plus ions, Cl minus ions, and you add it in water, what will the interaction be? Now we know that salt is soluble in water, right? But why it is soluble in water? Because it's same as water. It does interactions with water. It does intermolecular interactions with water. So let's look at the molecular level of sodium chloride. Sodium is positive, so you would see over here the positive ions. So the positive ions are representing the sodium, the Na plus, and then the negative ions, these are the green circles in there, these represents the Cl minus. And then you have the water molecule, right? So the water molecule is oxygen and two hydrogens, right? So we're going to represent it like this. This is an oxygen, it's bent. So it's oxygen and two hydrogens in here. The oxygen is more electronegative than the hydrogen. So this is why the oxygen is going to be a negative charge. So it's represented by a negative charge. And both of these hydrogens are represented by positive charge. So this is the same as this. Okay. The oxygen is the center, and the two edges, these are the hydrogens there. So now you have your charges of the oxygens and the hydrogens. So the thing is, how does water solvates the sodium chloride? Well, water is going to approach the sodium chloride. And remember, like dissolves like, and normally similar charges, they repel each other. Opposite charges, they attract each other. So for the water to dissolve the sodium, for example, you should have an interaction between the sodium and the oxygen, not the sodium and the hydrogen, because sodium is positive, right? So it needs to interact with a negative charge oxygen so that you would have what we call an ion dipole interaction. So the type of interaction here is an ion and it's a dipole. Why do we say dipole? We say dipole because we know that water is polar, right? And the term dipole, we give it for a polar center. So we know that oxygen is polar in there. These are covalent bonds. So this is going to be my dipole there. So it's going to be an ion dipole interaction. And this is the interaction here. So you're going to have an interaction between the oxygen and the sodium. And this is how the oxygen solvates the Na plus ion. Okay? At the same time, you have the Cl minus in there. So you have the Cl minus in the solution. The Cl minus are going to interact with the hydrogen because different charges, remember, they attract each other. Opposite, same charges, they repel each other. So different charges, they attract each other. Same charges, they repel each other. So over here, I would have an interaction between the hydrogen and the chlorine. And this interaction is the one that allows the water to solvate the NaCl. This is how sodium chloride dissolves in water, by having a ion dipole interaction between the sodium and the oxygen, and another ion, because the Cl is an ion dipole interaction between the Cl and the hydrogen. Those, they attract each other, and you are going to have the sodium chloride being solvated in water. Let's have another example. Okay, so let's have another example. Let's say, for example, if we have acetone in water. Okay, so what is acetone? Acetone is a solvent. And if I want to draw the structure of acetone in there, it's a C, it's a double bond O that is connected to a CH3 and another CH3 there. You don't need to know it's a structure, but here I'm just explaining why acetone is water soluble. And then you do have the water in there, okay? So again, we're going to go ahead and put the charges. And we say that water here is going to be negative and the hydrogens are going to be positive. And then we look at the C double bond O. This is the C double bond O of the acetone. Now the C double bond O of the acetone does have a polarity in there because it's a dipole. So see, this one has a polarity and the water has a polarity. So this one is a dipole and this one is a dipole as well. So this, I have two dipoles there. It's different than the first case where water had a dipole and the chlorines and the sodium were ions. So I had an ion dipole interaction. Okay, that's different. Here I do have no ions here. I don't have ions. I have a polar C double bond O and the polar HO bond. So I have a dipole-dipole interaction. Now how the interaction is going to be. Remember, opposite charges, they attract each other. Same charges, they repel each other. So because I do have a dipole between the C and the O is more electronegative, right? So the O now is going to be negative and the C is going to be positive in there. We say that these are partial charges, but I'm just going to write them as regular charges in there. Okay, so what I'm going to have here is that for the water to solvate the acetone, the oxygen in the water is going to interact with the carbon of the acetone in there. So this is how it is. Let me see if we can find it over here. So the oxygen in the water. So here you go. This is how it is. This is how they're representing the dipole-dipole interaction. So this is the C double bond O. Let's write it down as a C double bond O. So this is the C double bond O of the acetone. Okay, I'm only representing the C double bond O. The C is positive, the O is negative. So you're going to have a dipole-dipole interaction between the positive C and the negative O. Always the solvent wraps itself around the solute so that it dissolves it. And then the O of the acetone solute is going to interact with the hydrogen of the water, again, by a dipole-dipole interaction. So this is the interaction of the solute molecules with the water solvent so that the water can go ahead and solvate the acetone. Always remember, you guys, that a solute will not dissolve in a solvent if the forces between the solute particles are too strong to overcome by the interaction with the solvent particles. This means that if you have different phases, if you have an organic phase and an aqueous phase, definitely they are now going to interact with each other. So the solute will not dissolve in the solvent. So again, if the solute is present in an organic phase and the solvent is an aqueous phase, these are two different phases. Two different phases, and the forces are going to be really, really strong. So there will be no interaction between the solute and the solvent. So this means that the solvent cannot dissolve the solute. Point here is that solute dissolves the solvent. Solvent dissolves the solute whenever there's an interaction between them. So if there's no interaction between them, there will be no solvolysis in there. Solvent particles are more strongly attracted to each other than to the solute particles. And this is one way where the solute will not dissolve in a solvent. So the ideal case is whenever the solute interacts with the solvent. So if there's interaction with the solvent, then the solute will dissolve in the solvent. If there's no interaction, then the solute will not dissolve in the solvent. And always remember that likes dissolves like, always. So if you're working with a polar solvent, then polar solvents will dissolve polar solutes or ionic solutes, and nonpolar solvent will dissolve nonpolar solute or non-ionic solutes. There are two types of reactions, endothermic and an exothermic reaction. An endothermic reaction is whenever the solute and the solvent react with each other, and the system will absorb energy from the surrounding, causing the temperature of the solution to drop. So heat will appear in the reactants. Let's have an example in there, like for example, sodium nitrate. So let's study the dissolution of sodium nitrate, meaning that the solvolysis of sodium nitrate or solvating of sodium nitrate in water. How sodium nitrate dissolves in water. So the dissolution of sodium nitrate in there, we would say that it is endothermic. Why it is endothermic? Now, sodium nitrate will dissolve into its individual ions, which is the Na plus and the NO3 minus aqueous there. Okay, as you mix the sodium nitrate solid in water, you're going to see that the test tube becomes cold. Why it is cold? It's cold because it absorbs heat from the surrounding, and the solution temperature is going to decrease, and this is why you see cold in there. So this is why heat will be reported in the reactants, meaning heat is absorbed. So heat is absorbed. Another example is sodium nitrate. So any nitrate in there, that is an endothermic reaction. You just take a liquid, take water, add your solid in there of the nitrate solid, and then you're going to see that the temperature is going to drop. This is an indication that heat is being absorbed, and this is an example of an endothermic reaction. Because when heat is absorbed, we represent this by the energy of the reaction. And the energy of the reaction is called enthalpy, which is delta H. So delta H is the enthalpy of the reaction. And the enthalpy of the reaction with endothermic is always positive because heat is being absorbed. So it's always positive. Now for the exothermic reaction. Exothermic reaction is whenever you mix the solute and the solvent together. And when you do this, the system releases energy. So the heat now is going to show in the product, and this causes the temperature of the solution to rise. So you're going to see that when you mix the solute and the solvent together, your test tube is going to become hot. This means that energy is being released in there. Let's have an example like sodium acetate. So if we have sodium acetate, another one is NaOH. So sodium acetate. This is sodium acetate. Another one is NaOH. Same idea. So sodium acetate solid. It's going to dissolve in water. And it's going to dissolve into its individual ions, Na plus and CH3COO minus in there. These are the individual ions. The temperature of the solution is going to rise, and this is going to cause the delta H, which is the enthalpy of the reaction. This is the temperature of the reaction, to decrease. Okay, you're going to see that it decreases in there. So delta H is negative for an exothermic reaction. For an endothermic reaction, delta H is positive. So why delta H is going to decrease here? Because see, the acetate ion that you are forming, this will interact with water. So this CH3CO minus, this one is going to interact with water, and it will increase, because this is basic, so it will increase the pH of the solution. The solution is going to become more basic in this case. So the system is going to release energy, causing the temperature of the solution to rise. So bottom point here is that exothermic reactions, they do release heat, and then enthalpy of the reaction is negative. Endothermic reaction, they do absorb heat, and the enthalpy of the reaction is going to be positive.